The moon, our celestial companion, has captivated humanity for millennia. For centuries, it was believed to be a dry, barren world. But in the early 21st century, a series of groundbreaking discoveries shattered this long-held assumption, revealing a hidden truth. The moon harbors water. These revelations, made possible by advanced telescopes and robotic explorers, have ignited a new era of lunar exploration. The first hints of water on the moon emerged from spectroscopic observations which detected the signature of hydroxyl molecules in the lunar regolith. This discovery suggested the presence of water molecules, as hydroxyl is a component of water. Further evidence came from the Lunar Crater Observation and Sensing Satellite, or LCROSS mission, which intentionally crashed a spent rocket stage into a permanently shadowed crater near the lunar South Pole. The impact ejected a plume of material that was analyzed by LCROSS and other telescopes, confirming the presence of water ice. These findings revolutionized our understanding of the moon, transforming it from a desolate wasteland into a world with the potential to support future human exploration. Water is an essential resource for human life and has the potential to play a crucial role in enabling a sustainable presence on the moon. It can be used for drinking, growing food, and even producing rocket fuel. The discovery of water ice in permanently shadowed regions, where it is shielded from the sun's radiation, raises the tantalizing possibility of establishing lunar outposts that could serve as stepping stones for further exploration of the solar system. Moreover, the presence of water on the moon provides valuable clues about the history and evolution of the Earth-Moon system. The origin of lunar water is still a subject of debate, with several competing theories. Some scientists believe that it was delivered to the moon by comets and asteroids early in the solar system's history, while others suggest that it may have originated from volcanic activity within the moon itself. Understanding the source and distribution of lunar water can provide insights into the processes that shaped the early solar system and the formation of habitable worlds. It can also help us unravel the mysteries of the lunar water cycle, including how water is transported and stored on the moon's surface and subsurface. The discovery of lunar water has opened a new chapter in our exploration of the cosmos, presenting both exciting opportunities and intriguing questions. To delve deeper into these mysteries, NASA has developed the Lunar Trailblazer mission, a small but ambitious spacecraft designed to unlock the secrets of lunar water. Lunar Trailblazer, part of NASA's Simplex program, embodies the spirit of scientific inquiry, seeking to answer fundamental questions about our celestial neighbor. Equipped with advanced instruments, Trailblazer will embark on a mission to map the distribution, abundance, and form of water on the moon in unprecedented detail. It will focus on two key objectives: determining the form of water, whether it is hydroxyl, bound water, or water ice, and its distribution on the sunlit side of the moon, and characterizing the form and abundance of water ice in permanently shadowed regions. By studying the lunar water cycle, Trailblazer aims to shed light on the processes that have shaped the moon's surface and its potential to support future human exploration. This mission represents a critical step in our ongoing quest to understand the moon, our nearest celestial neighbor, and its role in the grand tapestry of the cosmos. Unlike Earth, with its vast oceans, rivers, and rain clouds, the moon's water cycle is a subtle and enigmatic process. The absence of a substantial atmosphere means that liquid water cannot exist on the lunar surface for extended periods. Instead, water molecules are thought to exist in a delicate balance between various states and locations. Some water molecules are bound to minerals in the lunar regolith, the layer of loose, unconsolidated rock and dust that covers the moon's surface. Others may exist as hydroxyl, a molecule that contains one hydrogen atom and one oxygen atom. Still, others may be frozen as water ice in the permanently shadowed regions at the lunar poles, where temperatures remain perpetually below freezing. The lunar water cycle is driven by a complex interplay of factors, including solar radiation, temperature variations, micrometeorite impacts, and the moon's interaction with the solar wind. Understanding this intricate cycle is crucial for determining the origin and evolution of lunar water, as well as its potential for supporting future human exploration. Section 2. Internal Origins, Water from Within. One of the leading theories for the origin of lunar water suggests that it originated from within the moon itself. This theory proposes that water molecules were trapped within the lunar interior during its formation billions of years ago. Over time, volcanic activity may have released some of this water to the surface, where it was incorporated into the lunar regolith or lost to space. Evidence supporting this theory comes from the analysis of lunar volcanic glass beads, which have been found to contain trace amounts of water. These beads, formed during volcanic eruptions early in the moon's history, provide a glimpse into the composition of the lunar interior. The presence of water in these beads suggests that the lunar mantle, the layer beneath the moon's crust, may contain significant amounts of water. However, the exact amount of water present in the lunar mantle remains uncertain. Further exploration and analysis of lunar samples are needed to determine the extent to which internal sources have contributed to the moon's overall water budget. Section 3. External sources, cosmic delivery service. Another plausible explanation for the presence of water on the moon is that it was delivered from external sources such as comets and asteroids. These celestial objects are known to contain significant amounts of water ice, and impacts from these objects could have deposited water on the lunar surface over billions of years. The moon's lack of a substantial atmosphere means that even small impacts can deliver water to the surface without it being vaporized by atmospheric friction. Over time, these impacts could have accumulated significant amounts of water, particularly in the permanently shadowed regions where it is protected from the sun's heat. The composition of lunar water, particularly the ratio of deuterium to hydrogen, provides clues about its origin. Deuterium is a heavier isotope of hydrogen, and the ratio of these isotopes in water can vary depending on its source. Measurements of the deuterium to hydrogen ratio in lunar water are consistent with a cometary origin, supporting the idea that impacts from these icy bodies have played a significant role in shaping the moon's water inventory. Section 4. In situ. In addition to internal and external sources, water may also be formed directly on the lunar surface through a process known as in situ formation. This process involves the interaction of solar wind protons with oxygen atoms present in lunar minerals. The solar wind is a stream of charged particles constantly flowing from the sun, and when these particles interact with oxygen-bearing molecules, atoms can then combine with hydrogen ions from the solar wind to form hydroxyl OH molecules. Over time, these hydroxyl molecules can further react to form water molecules. While in situ contributor to the moon's overall water budget compared to internal and external sources, it highlights the dynamic nature of the lunar surface and the variety of processes that can influence the presence of water. The relative contributions of internal, external, and in situ sources to the moon's water budget are still being Trailblazing, a path to discovery, the genesis of a mission. The Lunar Trailblazer mission represents the culmination of years of scientific inquiry and technological innovation, driven by the desire to understand the moon's water resources and their implications for future exploration. The mission's origins can be traced back to the early 21st century, when the discovery of water on the moon sparked a surge of interest in lunar science. As scientists began to unravel the complexities of the lunar water cycle, it became clear that a dedicated mission was needed to map the distribution, abundance, and form of water on the moon in unprecedented detail. In response to this need, a team of scientists and engineers at NASA's Jet Propulsion Laboratory, JPL, and the California Institute of Technology, Caltech, developed the concept for Lunar Trailblazer. The mission was selected by NASA in 2019 as part of the Simplex program, which focuses on small, low-cost missions that can address compelling planetary science questions. Lunar Trailblazer exemplifies the Simplex philosophy, demonstrating that significant scientific advancements can be achieved with a streamlined design and a focused set of objectives. A triumph of miniaturization, Lunar Trailblazer's compact design. Despite its ambitious scientific goals, Lunar Trailblazer is a remarkably compact spacecraft, a testament to the ingenuity of its designers and the advancements in miniaturized spacecraft technology. The spacecraft's bus, The main body that houses its instruments and subsystems is roughly the size of a golf cart, measuring just a few meters in length and width. This compact design is essential for keeping the mission's costs and development time to a minimum, allowing it to be launched as a secondary payload on a larger mission. Despite its small size, Lunar Trailblazer is equipped with everything it needs to carry out its mission, including solar panels to generate power, a propulsion system to adjust its orbit, and a sophisticated communication system to transmit data back to Earth. The spacecraft's instruments, though small, are highly capable, designed to make precise measurements of the Moon's surface composition and temperature. The combination of a compact design and advanced instruments makes Lunar Trailblazer a powerful tool for lunar exploration, demonstrating the potential of small spacecraft to make big discoveries. Peering into the lunar water cycle Trailblazer's scientific instruments. At the heart of Lunar Trailblazer's scientific capabilities are two sophisticated instruments, a high-resolution infrared spectrometer called the Lunar Thermal Mapper, LTM, and a multispectral imaging system known as the High-Resolution Volatiles and Minerals Moon Mapper, HVM3. Working in tandem, these instruments will provide a comprehensive view of the Moon's water resources. The LTM, developed by the University of Oxford, will measure the Moon's surface temperature with unprecedented precision, allowing scientists to identify regions where water ice is most likely to be stable. These temperature measurements will also be used to study the thermal properties of the lunar regolith, providing insights into the processes that govern the lunar water cycle. The HVM3, developed by JPL, will map the distribution of water and other volatiles on the Moon's surface by analyzing the sunlight reflected from the lunar surface. By measuring the wavelengths of light absorbed by different minerals, HVM3 can identify the presence of water molecules and determine their form, whether they are bound to minerals, present as hydroxyl, or frozen as water ice. Section 4. A collaborative endeavor. The Trailblazer team and international partners. The Lunar Trailblazer mission is a testament to the power of international collaboration in space exploration, bringing together the expertise of scientists and engineers from multiple countries. The mission is led by Caltech and JPL, with contributions from institutions around the world, including the University of Oxford in the United Kingdom, the Korea Astronomy and Space Science Institute in South Korea, and the Japan Aerospace Exploration Agency, or JAXA, in Japan. This international partnership reflects the global significance of lunar exploration and the shared desire to uncover the Moon's secrets. The diverse perspectives and expertise contributed by each partner institution have been essential to the mission's development and will be crucial to the analysis and interpretation of the data collected by Lunar Trailblazer. The mission's findings are eagerly anticipated by the international scientific community and are expected to have far-reaching implications for our understanding of the Moon and its potential to support future human exploration. Lunar Trailblazer embodies the spirit of scientific curiosity and international cooperation, paving the way for a new era of lunar discovery. Section 1. Objective 1. Mapping the distribution of water in the Sun's embrace. Lunar Trailblazer's first objective focuses on the sunlit regions of the Moon, where the constant bombardment of solar radiation creates a challenging environment for water to persist. While previous missions have detected hints of water in these regions, Trailblazer aims to provide a comprehensive understanding of its distribution, abundance, and form. To achieve this, Trailblazer will leverage its high-resolution volatiles and minerals moon mapper, or HVM3. This advanced instrument will analyze the sunlight reflected from the lunar surface, searching for telltale signs of water molecules. By measuring the wavelengths of light absorbed by different minerals, HVM3 can differentiate between water bound to minerals, present as hydroxyl, or existing as water ice. This detailed mapping will reveal whether water is evenly distributed across the lunar surface or concentrated in specific regions. Identifying areas of enhanced water concentration could provide valuable clues about the processes that deliver or form water on the Moon. For instance, if water is found to be associated with specific geological features, such as volcanic vents or impact craters, it could point to their role in the lunar water cycle. Furthermore, by comparing the distribution of water in sunlit regions to that found in permanently shadowed areas, scientists can gain a more holistic understanding of how water is transported and stored across the moon's diverse environments. This knowledge is crucial for assessing the moon's potential as a resource for future human exploration. Section 2, Objective 2, Unraveling the Lunar Water Cycle's Rhythms. Lunar Trailblazer's second objective delves into the dynamic nature of the lunar water cycle by investigating the temporal variability of lunar volatiles. This means studying how the abundance and distribution of water and other volatile compounds on the moon's surface change over time. Previous observations have hinted at intriguing fluctuations in lunar water signals, particularly in response to meteoroid impacts and solar wind exposure. Trailblazer will conduct systematic measurements to confirm and characterize these variations, providing insights into the processes driving these changes. Trailblazer's instruments will monitor select lunar regions over multiple lunar days and nights, allowing scientists to track how water signals fluctuate with temperature changes. By correlating these fluctuations with other factors, such as solar wind intensity and meteoroid impact rates, researchers can determine which processes have the most significant influence on the lunar water cycle. Understanding the temporal variability of lunar water is crucial for determining the stability of potential water resources. If water abundance is found to be highly variable, it could pose challenges for future lunar missions seeking to utilize these resources. Conversely, if certain regions exhibit relatively stable water levels, they could become prime targets for future exploration and resource extraction. Section 3, Objective 3, Delving into the depths of permanently shadowed regions. Lunar Trailblazer's third objective focuses on one of the most promising and enigmatic environments on the Moon, the permanently shadowed regions, or PSRs, found at the lunar poles. These regions, shrouded in perpetual darkness, act as cold traps, where temperatures remain low enough to potentially harbor vast reserves of water ice. Trailblazer will peer into these shadowed depths using its Lunar Thermal Mapper, or LTM, and HVM3 instruments. The LTM will create detailed temperature maps of the PSRs, pinpointing the coldest spots where water ice is most likely to be stable. This information is crucial for understanding the distribution and potential accessibility of lunar water ice. Meanwhile, HVM3 will search for the spectral fingerprints of water ice within these regions. By analyzing the faint sunlight that reflects off the rims of craters and other topographic features, HVM3 can detect the presence of water ice and potentially even determine its purity. These observations will provide unprecedented insights into the nature and extent of lunar water ice deposits. If Trailblazer confirms the presence of substantial water ice reserves in the PSRs, it would be a game-changer for future lunar exploration, potentially providing a readily accessible source of water for drinking, oxygen production, and even rocket fuel. Section 4, Objective 4, Deciphering the interplay of temperature and water abundance. Lunar Trailblazer's fourth objective centers on understanding the intricate relationship between temperature gradients and the distribution of water on the Moon. The Moon's lack of a substantial atmosphere results in extreme temperature variations, with surface temperatures swinging from scorching heat in direct sunlight to frigid cold in the shade. These temperature gradients play a crucial role in the lunar water cycle, influencing how water molecules move and interact with the lunar surface. Trailblazer will investigate this interplay by studying how the abundance and form of water vary with temperature across the lunar surface. The mission's LTM instrument will be instrumental in this endeavor, providing highly accurate temperature measurements of the lunar surface at various spatial scales. These data will be correlated with HVM3's measurements of water abundance and form, allowing scientists to create detailed maps that illustrate how temperature influences water distribution. This information will be crucial for understanding the stability of lunar water resources. For instance, if water ice is found to be present in regions that experience even brief periods of sunlight, it could indicate that these deposits are more transient than previously thought. Conversely, if water ice is found to be concentrated in the coldest, most stable regions, it would bode well for their long-term preservation and potential utilization by future lunar explorers. Section 1, Connecting the Dots. Trailblazer's contribution to lunar science. Lunar Trailblazer, poised to launch in the coming years, carries the weight of expectation for unlocking some of the moon's most closely guarded secrets. The mission's findings will extend far beyond simply confirming the presence of water, promising to reshape our understanding of the lunar water cycle and its implications for the evolution of the moon and other airless bodies in our solar system. Trailblazer's comprehensive dataset, combining detailed maps of water distribution, abundance, and form with precise temperature measurements, will enable scientists to connect the dots between various lunar processes. By correlating water abundance with geological features, surface composition, and temperature variations, researchers can gain insights into the mechanisms responsible for delivering, forming, and transporting water on the moon. For instance, Trailblazer's data could help determine whether the water found in permanently shadowed regions originated from cometary impacts, volcanic outgassing, or a combination of both. It could also shed light on the role of micrometeorite bombardment and solar wind interactions in replenishing or depleting lunar water reserves over time. Furthermore, by comparing the lunar water cycle to those of other airless bodies, such as Mercury and Ceres, scientists can gain a broader perspective on the processes that govern water distribution and evolution in the inner solar system. This comparative planetology approach could provide valuable insights into the early solar system's evolution and the factors that contributed to the habitability of Earth. Beyond its scientific contributions, Lunar Trailblazer will play a crucial role in paving the way for future human exploration of the moon. By providing a detailed assessment of lunar water resources, Trailblazer will help mission planners identify the most promising locations for establishing lunar outposts and utilizing in-situ resources. The mission's data on the abundance, distribution, and accessibility of water ice in permanently shadowed regions will be particularly valuable. If Trailblazer confirms the presence of substantial, readily accessible water ice reserves, it could revolutionize lunar exploration logistics. Water ice could be used not only for life support, such as drinking water and oxygen production, but also as a source of rocket propellant. The ability to extract water ice on the moon would significantly reduce the need to transport these resources from Earth, making lunar missions more sustainable and cost-effective. Furthermore, Trailblazer's detailed temperature maps of the lunar surface will be invaluable for selecting safe and suitable landing sites for future missions. By identifying regions with stable temperatures and favorable terrain, mission planners can mitigate risks and ensure the success of future lunar landings. Even as Lunar Trailblazer prepares to embark on its mission, the quest to understand lunar water is far from over. Trailblazer's findings are expected to raise new questions and inspire future missions to delve even deeper into the mysteries of the lunar water cycle. One area of ongoing research is the potential for subsurface water ice deposits. While Trailblazer will primarily focus on surface and near-surface water, there is growing evidence to suggest that significant quantities of water ice may be buried beneath the lunar regolith, particularly at higher latitudes. Future missions equipped with ground-penetrating radar or other subsurface imaging techniques could map the extent and depth of these buried ice deposits, providing a more complete picture of the moon's total water budget. Another area of interest is the isotopic composition of lunar water. By analyzing the ratios of different isotopes, such as deuterium to hydrogen, scientists can gain insights into the origin and evolution of lunar water. Future missions could collect samples of lunar water ice from different locations and depths, allowing for detailed isotopic analysis that could reveal whether lunar water originated from comets, asteroids, volcanic outgassing, or a combination of sources. Furthermore, the search for evidence of past or present liquid water on the moon continues. While the moon's current environment is not conducive to stable liquid water on the surface, there is evidence to suggest that liquid water may have existed on the moon in the past, potentially forming transient lakes or oceans. Future missions could search for signs of these ancient water bodies, such as sedimentary deposits or shorelines, providing valuable clues about the moon's early climate and potential habitability. As we stand on the precipice of this new era of lunar exploration, Lunar Trailblazer emerges as a beacon of scientific inquiry, illuminating the path forward. Its mission, though focused on a single celestial body, holds profound implications for our understanding of the solar system and our place within it. The moon, once considered a desolate and unchanging world, has revealed itself to be a dynamic and intriguing neighbor, harboring secrets that have the potential to reshape our understanding of planetary evolution. Trailblazer's findings will resonate far beyond the scientific community, capturing the imagination of a global audience eager to explore the cosmos. The prospect of finding readily accessible water ice on the moon sparks dreams of lunar outposts, scientific research stations, and even the possibility of one day utilizing lunar resources to propel us further into the solar system. The data collected by Trailblazer will serve as a cornerstone for future lunar missions, guiding the development of new technologies and exploration strategies. Its legacy will be measured not only in the scientific discoveries it enables, but also in the inspiration it ignites, encouraging generations to come to reach for the stars. Lunar Trailblazer represents a crucial step towards establishing a sustainable human presence on the moon. By mapping the distribution and abundance of lunar water, Trailblazer will provide invaluable information for selecting future landing sites, designing lunar habitats, and developing in-situ resource utilization technologies. The potential for utilizing lunar water ice as a resource for future human explorers is immense. Water ice can be processed to provide drinking water, breathable oxygen, and even rocket propellant, significantly reducing the need to transport these vital resources from Earth. This would drastically reduce the cost and complexity of lunar missions, making it feasible to establish a permanent human presence on the moon. Moreover, Trailblazer's findings will contribute to our understanding of the moon's potential habitability. While the moon's current environment is harsh and unforgiving, the discovery of abundant water ice raises intriguing possibilities about the potential for life to have existed on the moon in the past, or even to be present today in some form. The search for life beyond Earth is one of the most profound scientific endeavors of our time, and the moon, with its newfound potential for harboring water ice, has emerged as an unexpected but compelling target in this search. Lunar Trailblazer, with its mission to unlock the secrets of lunar water, paves the way for a future where humanity explores the moon, not just as a scientific curiosity, but as a potential second home.